let's say this molecule is there. We can think about what would happen if using that reagent or this reagent. And they almost look same, right? Except this is okay, this is OH. What is okay thing? That reagent is okay, that's good reagent. K is a precipitation, positive charge. O is oxygen, negative charge. It's a strong, it's a butoxide, that's a strong base. Would you consider this a strong profile? It is just, if you look at the O minus side, yes, that's a strong profile, but it carries the distributive groups. That's a turkey, too big. So this is not a good nucleophile. This just in a good base. So that only makes an E2, not SN2. This is an alcohol, weak reagent. So we should expect E1, SN1 with this. And then the reason I keep saying that this is secondary alkyl halide, right? Secondary alkyl halide. But the thing is, this secondary alkyl halide, I don't think it's going to go for the SN2 for the reason it has a tertiary position next to it. Remember that? If you have a tertiary subcarbon next to that, it will really make an SN2 reaction difficult, even though it's a secondary, even though primary. So this makes it this alkyl halide not a good substrate for the SN2, regardless of what you have. But the top side basically just guarantee you're not getting SN2 at all. Anyway, let's talk about what will happen. Both will make elimination reactions, but the thing is, are they making same elimination product? That is what I'm asking. They may not. So first thing is, elimination product, if you don't care about the mechanism, I'm pretty sure that you're going to think about, okay, just take the protons away from the adjacent carbon, let's make a double bond, right? I'm pretty sure that someone just patronized this in a problem-solving question. I can make a double bond between these two, I can make a double bond between the two. So this one or that one. But I hope that you remember that there is no hydrogen on this carbon. There's two alkyl chain, two methyl groups. There's no way you can make this one. These things are impossible. If you're just trying to make more substituted double bonds as a product, then you definitely get wrong here because these things are not possible. There's two methyl groups here, and then without removing the methyl groups by the base. So that's why you just don't try to make the most substituted double bond. That is not working. So this is only the product that you're going to get from these two. Compared to that, when you're using this, that's a different thing. I mean, most likely, not most likely, someone who doesn't understand the chemistry may say that if that was a product of these reactions, and that reagent almost looks same as that, so maybe we should get the same product. If you happen to think that way, then you're really underestimating organic chemistry. That's the point I'm making here. You really have to sort it out. Dark reactions are E2 elimination reactions, right? You pick up the proton in an adjacent carbon, which has to be transaxial, which is equivalent to the anti-covalent. The hydrogen trans to this, right? It has to be lined up. That protons are picked up, make a double bonds, and then that makes this product. If you do that with the alcohol here, you're not doing it. This doesn't get the proton. It doesn't have enough strength to pull up proton. So what happened? Molecules sit there for a long time, and then it's wait until the halide, the bromide, pops out. It makes a carbocation. I mean, once it makes a carbocation, these protons taken up by the base, you can potentially make that one too. But the thing is, that's a secondary carbocation. And of course, if you shift the hydrogen from this carbon to there, it just makes another secondary carbocation. So you may think that no rearrangement is possible, but not the hydrogen. Carbon can also shift too. If this carbon, one of these methyl groups shift there, it makes a tertiary carbocation. And then when the tertiary carbocation made it, then that's more stable. And then that's going to be basically making lots of elimination reactions. Proton can be come up from that, you're gonna have double bonds there. Proton can be come up there, you're gonna make a double bonds here. But the best one is this one. When this proton taken out, you make the double bond between there, which makes it tetrasubstitute double bond, the most stable ones. So out of these things, I'll probably say that would be the major. I mean that, if you think about the base come, pick up this proton, make a double bond, make the same proton you see there, it's not possible because of this, I mean, maybe a very small amount will be, not the major amount, really small amount. So depending on how you do it, you get different elimination product. That's something that you really have to think about. So don't just paralyzing, this problem solving, because there's plenty of things can go wrong. You just memorize, I'll just make a double bonds, and I'll make the most substitute double bonds. There's a plenty of things that can go wrong, which I'm going to show you in that slide too. So